welcome to today's VDMA shop floor data session with the topic of OPC UA for laser systems, the OPC 40530. I'm very happy that we have two experts out of the working group here to hold a presentation. We have Dr. Sven Breitung and Josef Pfaffinger. And please, I would ask you to introduce yourself for a second before you start with your presentation.
Yeah, thank you, Heiko. And welcome also from my side to all the participants. Yeah, I'm Sven Breitung. I'm the Managing Director of the VDMA Working Group Laser and Laser Systems for Material Processing. And I'm also the head of the VDMA Quantum Technology and Photonics Forum.
My name is Josef Pfaffinger. I'm Senior Software Manager here in Coherent Munich. In Coherent Munich, we are building systems, laser systems, and I'm part of the VDMA standardization cycles and initiatives. Thank you.
Perfect. Thank you very much. So as you can see, we have one expert from the VDMA or VDW, and we have one expert out of the industry. And I'm very eager now to listen about what OPC UA for laser system is all about, what the status of this companion specification is. And so I would ask you to start the presentation. The stage is yours.
Okay, thank you. Yeah, here's the agenda of today's meeting. Together with Josef, I will tell you in the VDMA shop floor data session OPC UA for laser systems, the background of the standard. I will start with a short introduction about the laser in general and how we are supporting the members of the VDMA with the working group laser and laser systems for material processing. In few slides, I will also want to give a brief insight into how OPC UA serves as the basis of a global production language and what the goals are. After the background, I will give an overview of the use cases and the reason for standardization. Josef will give from his industry perspective a deeper insight into the information model and an outlook of UMATI and live demo. So let's start with a laser. So laser stands for light amplification by simulated emission of radiation. So the history, let's start with the history. The concept of lasers was proposed by Albert Einstein in 1917, but it wasn't until the 1960s that the first working laser was developed. Since then, the technology has advanced rapidly. Lasers come in various types, including gas lasers, solid-state lasers, semiconductor lasers, dye lasers, and fiber lasers. Each type has unique properties and applications. Here are the applications. So first is the industrial manufacturing, so laser cutting, welding, marking, and engraving are common applications in industries such as automotive, aerospace, and electronics. For medical, lasers are used in surgeries, for example, for skin treatments or vision corrections, and various diagnostic procedures. In communication, fiber optic communication systems rely on lasers for transmitting data over long distances. In research and development, lasers are essential tools in scientific research used for spectroscopy, microscopy, and studying fundamental physics. And the last point, defense and security. So laser technology is employed in the defense systems for target designation, range finding, and as an energy weapon. So the VDMA working group Lasers and Laser Systems for Material Processing has currently 51 members from Germany, Switzerland, and Austria, and the members are supplier of components, laser manufacturers and system integrators, as well as research institutes and universities. On the picture, you can see the board of directors. The chairman of the board is Dr. Christoph Ullmann from Laserline. His deputy is Dr. Stefan Ruppig from Coherent. And also in the board is Nikolaus Meyer from Weil Technology and Dr. Hagen Ziemer von Trumpf. Yeah, networking is one of the essential parts of the association. And so the members are meeting twice per year. And the next meeting of the members will take place in Frankfurt am Main on November the 6th at the VDMA. In May 2025, we will also meet again at Weil Technology. So here you can see the summary of what we do. In a nutshell, we offer the members a network and networking opportunities, as well as the opportunity to recognize market trends together at an early stage. We provide market data and analysis and carry out industry-specific press work. We are active in the area of trade fairs and conferences. For example, we are the conceptual sponsors of the world's leading trade fair, Laser World of Photonics, which will take in Munich again in 2025. In addition to providing technical and legal advice to members, we are also active in promoting research and standardization. And under this topic, today we report on the development of the OPC UA interface standard for laser systems. The advantages of a membership, you can find those information with a QR code or with a link, which is in the presentation. Yeah, at the heart of the fourth industrial revolution, also known as Industry 4.0, smart manufacturing is transforming modern manufacturing operations. Smart manufacturing integrates advanced technology, such as the Internet of Things, automation, and artificial intelligence, so AI, into existing workflows, enabling organizations to optimize optimize performance throughout the manufacturing lifecycle. Here you can see the major goals. So the smart production needs simplified interfaces, simplified integration into the shop floor, and simplified access to standardized production data. For this, we need standards, a global production language. The Industry 3.0 started with proprietary communication. And with the Industry 4.0, we introduced the mesh communication network with the OPC UA. So OPC UA serves as the basis for the global production language. And here you can see the advantages of OPC UA, like open source and that it's secure. Also possible are various protocols, semantic machine description, and it's scalable. The VDMA is working on the domain-specific harmonized information models with the development of OPC UA companion specification. So in total, 40 active working groups developed and involving those companion specification like we did for laser systems. The VDMA is also working on the cross-domain harmonized information models with OPC UA for machinery. And OPC UA laser systems, therefore, based on the cross-domain harmonized information models OPC UA for machinery and on OPC UA for machine tools. Other companion specifications like here woodworking are only based on machinery. Here you can see the harmonized information in OPC UA for machinery, like the machine and component identification, which you will also see as a use case for OPC UA for laser systems. Our initiative for OPC UA for laser systems started with a white paper, which identified 8 use cases, which you can see on the right-hand side, on the lower part, which specifically, those 8 use cases are specifically for the laser systems. So after the publication of the white paper, we received positive feedback from major customers of the beam source manufacturer, Coherent Laserline and Trumpf. And so the work on a companion specification began in November, December 2022. The goal was to create an international accepted standard. So shortly after the start, we collaborated with the OPC UA, the OPC Foundation. The use cases describe possible usage scenarios of the interface and the added value that can be achieved. The use cases are described from the view of a maintainer. Now we look at all the 8 use cases individually. So for the use case laser system running or not running, it should be possible to see at a glance which device is running, not running, or is in a fault condition. If the laser is in a fault condition or not running, the maintainer can easily identify the reason, so that in the event of an unscheduled loss of production, quick actions can be taken. The parameters listed are to be used to create the added value described in the use cases. So for the use case laser systems running or not running, the parameters are running, so if the laser system is running or not, the status, so the mode in which the laser system is, and the information about the fault condition or not running. This variable can provide additional information about the cause. So for the use case errors and warnings, the maintainer can see on the interface the errors and warnings and can react to malfunctions and identify the error causes. So here you can see the parameters listed are the message, the code, the severity, which is an indication of the urgency of the event, the component in or for which the message was created, and the timestamp. For the use case information about the next maintenance, the interface displays a forecast of the next manual intervention to be performed on the laser systems, and so the maintainer can optimize and plan the next activities on the laser systems. The parameters are the next maintenance, when this maintenance should be carried out, the component for which the message was generated, the description of the maintenance to be carried out, the code, and the operating hours. For the use case uniform identification of laser systems, the use case provides a digital nameplate, a nameplate of the laser system displaying basic and static information. Activities within a heterogeneous machinery pool not only consists of laser systems, are simplified for end users of this interface. And so the parameters in the next two slides are predefined by the OPC UA for machinery. So it's the production instance URI. So an URI is a unified resource identifier. The parameter also includes manufacturer, the manufacturer URI, the model, the production code, and the software revision, as well as the serial number, the year of the construction, the asset ID, the component name, and the location. So for the use case recipe settings and overview, the interface provides a list containing all available recipes and information about the specific recipes. The maintainer can keep the laser system updated and ready for its intended usage. This information can also be used by the maintainer to identify unused recipes in order to manage the storage capacity efficiently. So here you can see the parameters. So the parameters are the recipe name, the recipe number, the timestamp, the recipe revision, the recipe content, the counter, and the last use. For the use case activity logging information, this should help the maintainer to easily track configuration changes, which is useful to identify possible error causes. The parameters are change. So this parameter contains the description of the change. This can include the value before and after the change, and also the timestamp. With the use case condition data monitoring, the maintainer monitors the system condition data like the current temperature or the power consumption to analyze correlation between different variables from multiple sources like sensors. So here you can see the parameters. Some of them are thresholds to start an error or warning message. So you can see here the upper warning level, the lower warning level, the upper error level or the lower error level, but also the parameter name, the timestamp, the unit of the parameter, the value of the parameter, and a description. With the use case consumption data, the interface provides information about the consumption of various external media, for example, the power consumption, the compressed air, cooling water in a standardized way. So the parameters are the name, the timestamp, the unit of the parameter, the value of the parameter, and a description. So these were the 8 use cases. I already told you that we started the project towards a companion specification end of 2022. And until May 2023, we had 7 meetings with a core group and 4 meetings with the total working group laser systems. So the total working group was chaired by Josef Pfaffinger, and here you can see the members. It consists of 40 experts from Europe, India, Japan, Mexico, and the US. The companion specification was published in December 2023 by the OPC UA Foundation and in February 2024 by the DIN. Yeah, this was my part, and now I hand over to Josef, who will give a deeper insight into the information model and an outlook of UMATI and live demo. Josef, the stage is yours.
I switch on my micro and take over the control. If you would give me the control, I could control the micro. Thank you.
You are in control.
Got it. Thank you. Thank you, Sven, for this great introduction into our topic. And I take over here. Let's see if my control is working. Okay. I go back to the total working group, and I just would like to thank the University of Stuttgart, because they were supporting us in the formal creation of this information model. This is a lot of work, and they have a lot of OPC background, so thanks to the University of Stuttgart. And another hint here is, as a chairman of this total working group and the core group, I also represent the laser group in the VDMA interoperability and harmonization initiatives. And we will see later why harmonization of those standards is a key factor in the machine industry. So going to the next slide. Here, maybe the note is, please use the QR code or the URI on the left side. This will direct you directly to the download page, and you can download the whole specification in a PDF form. So please use the QR code to download the specification. So here again, we see the important goals, which we already saw. I just want to give you some evidence of the goals, how we can achieve the simplified interface, the simplified integration, and the simplified access, and what we mean with the global production language. So let's get started with a good question. And the question is certainly, why do we need an additional specification for a laser system? And we already heard about the high flexibility of a laser system because it's photonics. So we can adapt very, very quickly to different materials like metal, glass, plastic, even wood. So we have really an important tool, and this tool is part of many factory processes. And one challenge is that usually the laser is integrated in subsystems, or as a subsystem, sorry, in machine tools, as a subsystems, or in larger machines, or even in inline housings. And the obvious solution for this is to use the OPC UA information model for machine tools, as we have seen it, and we see what it means. So if you build an instance of the laser system, you are using building blocks from the machine tools, and so this fits perfectly into larger machines. And we saw examples in the use cases. For example, the unified identification of machines is really the same in between machine tools, or the system is running or not running. This is also a very common use case. And technically, this is done through referencing, which means you create a laser interface based on an existing namespace like the machine tools or machinery, if you go on a broader machine. And even mining you could do even application in the mining industry if you use the machinery as a basic namespace or model. From here, now you start to implement your specific behavior of the laser. And this is done through inheritance or referencing the machine tools and machinery specification, and add on your laser specific data, which we have seen in the rough description of the use cases. So here is the big view of the use cases. And this is the big view of the interoperable information models, like Sven already showed. All those are based on machinery, or the laser in special is based on machine tools. And this makes Industry 4.0 really easy. The easier the sharing of information, the more efficient is the work. And again, this is, I'm sorry. This is a major goal in our in our list of goals. So on the right, we see all these specifications, which are standard publications with their dates when they have been released. We have measuring tools, metal forming, joining, and so on. So all those specifications are building a complete smart factory. And the laser has been specified since February 2024. And this is a shared language concept and gives us the ability to reach the overview, the interoperability of all the systems which are based on these machine tools. And now we look at the question why OPC UA standard can reduce costs. I mean, if we look at other universal interfaces, for example, our old E27 light bulb socket, everybody knows that, or our more modern USB interface, we see very different functions, such as keyboards, mouse, monitor on the light bulb, LEDs, modern LEDs, whatever you can think of. Every function is delivered with the same interface, with a universal interface. And everything is interoperable and independent of manufacturer or vendor. So OPC UA is just as universal like a light bulb. And the laser industry uses this universal standard like many other industries are using it. And so from this OPC UA specification, the laser specification is using the same sockets. So every vendor and integrator and even end user saves development cost from equipment up to the factory. So all are using the same information model. And let me make one thing clear here. The competition is not in the interface definition, like in USB, everybody's using it, but in what you do with the data and how you use the data. And we will see in the next slides how we use the data. So, as Sven mentioned, our goal or challenge is to define the global production language. A challenge that we are taking a closer look now. So technology-wise, we define our laser information language in objects, attributes, methods, and relations. And all this is formally described in OPC 4530, which is our companion specification for laser systems. And that is the basis on which systems communicate with each other in the sense of really a uniform language. Also here, a comparison to a famous standard like Bluetooth is possible. All devices describe themselves in a uniform way and communicate with the host without changing the setup routine, despite very different functions, like mouse, keyboard, everything. Even lasers are connected via Bluetooth. So we in the machine industry, we call it UMATI, our universal language. We call it UMATI, Universal Machine Technology Interface, into which the OPC UA laser fits in a way to deliver its data or to access data in a very standardized way in any production. And this is one of our major goals, simplified access to standardized production data. And now we will look at an example use case, which we already have seen in the first entry slides. And this use case certainly is relevant for all machines in a factory because you want to know the state of your machine. And Daniel, the user, Daniel wants to check the status of these 3 laser systems of 3 different manufacturers or vendors, and he sees the status on his dashboard. The developer, or let me say, each developer of the laser interface has to download the companion specification for laser systems from the OPC Foundation website. He uses an OPC UA programming interface that can handle companion specifications. There are a few of them on the market. And the laser system states, for example, are defined in table 2020 of this companion specification. And so he can display the laser specific states on the laser dashboard. And since the companion specification is structured also in XML, not only in a written text or a human readable text, it can be easily loaded into the programming environment and filled with your real-time data. And we saw the real-time data, we saw the status, and we saw the monitoring data, which we can provide individual for each laser. So with a minimum effort, you implement a standardized data connection for laser systems. And that's the example use case, and maybe one of the most important because it's similar to the light bulb in every system. So now we come to the demo video. It's not a live demo, it's a demo video. And we took this demo video during our last common laser World of Photonics together with the VDMA, and we showed this demo video to the audience. And while I'm starting this video and you are watching this video, I can give you, can you see the video? Yeah, okay. I can give you an outlook what we are planning. We are planning a central dashboard for the Laser World of Photonics 2025 with real connected laser systems from as many laser exhibitors as possible. And we will show on a centralized dashboard hosted by VDMA all the different laser machines and maybe other automation machines. So this showcase should demonstrate where we are during the Laser Show 2025 with our universal machine tool interface.